In this question, we're going to use the substitution of u being 5 to the power of x. Now again, 5 to the power of 2x would be 5 to the power of x all squared. So u the squared would be 5 to the power of x all squared. So we can do that substitution in that part. We've got the 5 to the power of x, so that becomes u minus 20, and it's all equal to 0. We factorise. So 4 times minus 5 gives us minus 20. We get the 4 minus 5 plus 4 gives us minus 1. That will leave us u plus 4 would equal 0, or u would equal minus 4. Now we saw before that 5 to the power of x in this case can never equal minus 4, so we get no solutions. From this part, u is going to be equal to 5 because something there has got to make it equal to 0. U would equal 5. U is equal to 5 to the power of x, gives us 5 to the power of 1, which means x is equal to 1. Only solution there. No solutions here, only one solution for this equation. This one's a little bit tricky because you've got 9 to the power of x and 3 to the power of x. Again, just relies on you playing around with your arithmetic here. 9 to the power of x can be written as 3 squared, all to the power of x, which can be written as 3 to the power of 2x. Playing around with our indices gives us 3 to the power of x, all squared. So if we let u be equal to 3 to the power of x, 9 to the power of x is 3 to the power of x all squared, and then 3 to the power of x is u. That gives us 9 to the power of x being u squared. 3 to the power of x is u, and we've got minus 12. We've got u plus 4, u minus 3 is the factorisation of that quadratic. U plus 4 would leave us to u equal to minus 4, and 3 to the power of x in this case, sorry, cannot equal minus 4. No solutions from that part. U minus 3 leads us down to, it being equal to 0 leads us to u equal to 3, or 3 to the power of x equals 3 to the power of 1, and x is equal to 1. Playing around with the indices is the key here. If you can't get that manipulation, you're not going to be able to get to that quadratic to be able to solve it. So be wary of what needs to be done there. This one's a little bit different. X plus 1 on x all squared. Now what I'm going to do is, I can see a squared there. If I can make a substitution there, I'm going to get u squared plus u minus 2 is equal to 0, because I'm going to have a substitution of u being x plus 1 on x. Makes life a little bit easier if I can, in a little bit nicer quadratic than that quadratic that we can see there. You can see x plus 1 on x becomes u. We've got a minus 2 in there. Once I've got to that point, that's a nice simple quadratic to solve. U plus 2, u minus 1 is our factorisation. Now, if I've got u plus 2 is equal to 0, doing the substitution back of x plus 1 and x plus 2 means I've got a quadratic here. Because I'm going to multiply through to get rid of that denominator. That gives me x squared. That one will just become 1, and we get 2x. Now if we have a look there, that's a perfect square. X plus 1 all squared is x squared plus 2x plus 1. If that's the case and that's all equal to 0, x would have to be equal to minus 1. There's the only solution there. In this situation, we've got u minus 1 is equal to 0, so I'm going to multiply through by x. Gives me x squared minus x plus 1. Now, you could try and do the quadratic formula, but through experience, I'm looking at this one going, I can't find something that factorises nicely, which we would expect it to do, but not necessarily. But if I investigate the discriminant, I see the discriminant's less than 0, well, that means I don't have to go any further. If you do the quadratic formula, you'll just end up with a negative under the square root, which means you'll get no solutions. X is equal to minus 1 is the only solution in this situation.